Hi everybody, this is Math 026 for Hartford Community College, and this is Module 4, Part 2, where we're going to look at composite functions, and inverse functions. Function composition is evaluating a function at another function. So you'll see when we do function compositions, you'll see this kind of silly little open circle, or it looks crazy. It looks like with F and G, it looks like fog. But what this stands for is F composed with G, and it's the composition of functions. So it's basically we take the function of F and we substitute G, that G function in wherever there's a variable in F. And the domain of the composition of the function is all the values in the domain of G such that G is in the domain of F. So we kind of look at the domain of those combined functions. So what we're going to do here is we're going to start by looking at F composed with G of x. So F of x here is 2x squared plus 1, and G is 5 minus x. So if we do F composed with G, really what we're going to do is we are going to take G, because it's listed second, and plug it into the x on F. So it will end up looking like it will be 2 times 5 minus x, you keep that squared there, plus 1. And then we do need to do the simplification to simplify it. I can square the 5 minus x, so I'll do 2 times 5 minus x times 5 minus x plus 1. And I'll distribute that 2 to this term first, or this factor. So it will be 10 minus 2x times my 5 minus x plus 1. So now I'm going to FOIL. 10 times 5 is 50. 10 times negative x will be negative 10x. Negative 2x times 5 is negative 10x. And negative 2x times negative x will give me positive 2x squared plus 1. And then we're going to combine like terms and write it in descending order. So I'm going to start with that 2x squared. I'm going to put it first. Then I'm going to look for my x terms. So negative 10x and negative 10x will give me negative 20x. And then I do have 50 plus 1, so plus 51. And that would be my final answer there. Now we are going to do G composed with F of x. So now we're going to take and insert F, because it comes second, into G where the variable is. So now I'm going to have 5 minus, instead of x, I'll put 2x squared plus 1. And we do want to simplify this here if we can. And really what we're going to do is distribute that negative outside the parentheses. So it becomes 5 minus 2x squared minus 1. And then it's going to equal, I'll put it again in descending order, so negative 2x squared. And 5 minus 1 will be plus a positive 4. And that will be my final answer there. Now, our final one here is F composed with F of x. So what we are going to do there is we are going to start with F and then plug F back into the problem. So we're going to have 2. And where that variable is, I'm going to plug in F again. So 2x squared plus 1 squared plus 1. And we do need to simplify this by FOILing 2x squared plus 1. So we're going to have 2 times 2x squared plus 1 times 2x squared plus 1, and then plus 1 on the outside. So I'm going to multiply that 2 times the first binomial. So it will give me 4x squared plus 2. And now I have to take that expression and multiply it times my 2x squared plus 1, and keep that plus 1 there. So this is going to give me, when I FOIL, 4x squared times 2x squared is 8. x to the 4th power. 4x squared times 1 will be plus 4x squared. 2 times 2x squared will give me another 4x squared. And then 2 times 1 will give me plus 2, and then we have that plus 1. So now we're going to combine our like terms, and that is going to be 8x to the 4th power plus 8x squared plus 2 plus 1 is 3. So 8x to the 4th power plus 8x squared plus 3 is our final answer there. We're going to practice more composition of functions here. So now we have f of x is defined as the cubed root of x minus 1, and g of x is x cubed plus 1. So first we're going to start with f composed with g. So f is 3, and then it's the square root of x minus 1. But instead of that x, I'm going to plug in g. So it's going to be x cubed plus 1, and then minus 1. So we can do some simplification here. We can simplify underneath that radical. We have x cubed plus 1 minus 1. And I know that 1 minus 1 gives me 0. So it leaves me with the, oh, and this is the cubed root here, the cubed root of x cubed. And again, that equals a 0. And the cubed root of x cubed equals x. So when we plug that in, or we do that simplification, we end up with just a single x there. Now let's try g composed with f of x. So we're going to start off with g, which is x cubed. So we're going to do this. We're going to do, instead of that x, we're going to put in f. So it's going to be the cubed root of x minus 1 cubed, as I just plugged this into x cubed plus 1. Now, we know if we have the cubed root and we cube it, we end up with just what's underneath that radical. So we have x minus 1 plus 1, and that will simplify to x. Now, this is a good example to look at. Sometimes they will both simplify to x, and what this means, and we're going to talk about this more in the coming slides, but these two functions are inverses of each other. And we know they're inverses because if we do the composition of each, and we do f composed with g and g composed with f, and they both simplify down to a single x, that means that they are inverses of each other. So keep that in your mind when we talk about it later on. Okay, so now we're going to finish up, do a little bit more composition. We are going to start with f composed with g of x. And f is 1 over x, and g is 1 over x plus 2. So now I'm going to have 1 over, and instead of x, I'm going to put in there 1 over x plus 2. Now, this is similar to a division problem with fractions, or it's written like this. We really have 1 divided by 1 over x plus 2, or divided by, yep. And remember, when we multiply or divide fractions, we actually multiply by the reciprocal. So we're going to do 1 times x plus 2 over 1, which again, that 1 we could turn into a fraction by putting 1 underneath. So when we go straight across, we end up with x plus 2. And we could put it over 1, but we don't need to. So our final answer there is x plus 2. Now for g composed with f, g is 1 over x plus 2. But instead of this x, I'm going to put in 1 over x plus 2. And for this one, because we have that expression there, we could either add those fractions on the bottom, or I'm going to clear my equation of the fractions. So to do that, x is my only denominator. I'm going to multiply every single thing by x, so I can clear my equation of fractions. And when I do that, it's going to give me x on the top. If I do 1 over x times x, and you can put it over 1, those x's cancel out. It equals a 1 plus 2 times x will give me 2x. And here, we don't have a radical, So we really can't, we don't have anything where we, anything we can't do here to simplify, or we can do to simplify it. That domain on the bottom, we do have to worry about the domain here because we have an expression on the bottom. And so the domain here, remember when you have a fraction, you can't have that denominator equal to 0. So the domain will be all real numbers except whatever turns this equation into 0. So if I solve this equation for x equal to 0, I'm going to end up with 2x equals -1 divided by 2. So the domain for this one is going to be all real numbers except x cannot equal -1/2. Now for a, we don't have a radical and we don't have a fraction. So my domain for this one can be any real number. All right, so the next thing we're going to talk about, and this will be what we will talk about for the next few slides, it'll be the end of this section, is going to be inverse functions. And I briefly talked about it when we were doing composite functions because we did one that showed us the two equations were inverses. And what an inverse is if you have a function that has a domain of D and a range of R. The inverse, I always think of it as like reverse or invert. And then if you have the inverse of that function, then the domain is going to be what was the range in the first problem, and the range is going to be what the domain is. So they switch the domain and the range when you have the inverse. The notation that we use to show that it's an inverse is we have f of x for the function and then f of -1 of x. So that's not an exponent, that is notation to show that it's the inverse function. And again, the two domains and range switch between the function and the inverse, so they would flip-flop between the two. And you can kind of see here, we have a diagram that depicts the domain and the range of the function 2 of x, or 2x, and again, the domain and the range flip-flop between the two. So to verify functions are inverses. We did that earlier with our composite functions. What we are going to do is if we have two functions and we don't have the graphs to look at or ordered pairs or anything, we are going to do the composition of each. And if f composed with g of x and g composed with f of x both simplify down to x, the two functions are inverses. And then if you have ordered pairs or look on a graph, for every ordered pair for the original function, the point that corresponds to it on the inverse should be the opposite of that. It should be y first and then x. And again, we'll take a look at both of those. So here they're asking us to prove that these are inverses of each other. So the first thing we're going to do with A is we have a set of ordered pairs. So f of x, the first ordered pair is 2, 1. Then we have 5, -3, and 6, 8. And here with ordered pairs, remember the x and y values should be switched. So for g of x, instead of 2, 1, I have 1, 2. I have -3, 5, so they switch those two order pairs. And then I also have 8, 6. So again, those are swapped. So these two are inverses of each other because g of x has the opposite, like x and y are swapped from f of x. So that one was nice and easy because you just look at the ordered pairs and see if they're swapped. Now for B, because we have two expressions or two functions here, we're going to have to do our composition of each. So I'm going to have to do f composed with g of x and also g composed with f of x. So first, f is x plus 5. So instead of x, I'm going to plug in my x minus 5 and then keep my plus 5. Now this is kind of nice and easy because when I go to simplify it, those 5s cancel out and we're left with just x. Then for the next one, g is x minus 5. So I'm going to plug this in for x. So it's going to be x plus 5 minus 5, which will simplify to just, again, x. So f of x and g of x here, because when you do the composition of each, both simplify down to x. They are inverse functions. All right, let's take a look at C, and we are going to, again, do the composition. We'll do f composed with g of x, and then g composed with f of x. So f composed with g of x is going to be f is the 5th root of 3, and instead of x, I'm going to put x to the 5th power plus 1 divided by 3 minus 1. So now I need to do the work underneath there under that radical. And remember that 3 times the expression is really like 3 over 1. So those 3's will cancel. And that leaves me with, right now, x to the 5th power plus 1 minus 1. X, or 1 minus 1 will give me a 0. So now I have the 5th root of x to the 5th, which we know will simplify to x. So it worked that way. Let's try g composed with f of x. So g is x to the 5th power. So we have, instead of x to the 5th power, we're going to put in there f. So it's going to be the 5th root of 3x minus 1 plus 1 all divided by 3. And we do need to, I forgot one part there, because it's x to the 5th power up here. It's going to be, this is going to be to the 5th power. So the nice thing here is because we have the 5th root and then we have that 5 there, that's going to like cancel each other out. So we're going to end up with 3x minus 1 plus 1 over 3. And then I know negative 1 plus positive 1 equals a 0. So right now we have this. We have 3x over 3. But those 3 equal a 1, and we end up with just x. So these two functions are inverses of each other, because when you do the composition both ways, it does simplify to an x. All right, let's look at D. So f of x is x over x plus 1, and g of x is x over 1 minus x. So if we do f composed with g of x first. So f, we are going to have, this is going to be a doozy. So we're going to plug in g for x. So it's going to be x over 1 minus x over, and then where that x is, we're going to have x over 1 minus x plus 1. Now, for this one, this is solving our complex fractions, which is something we did in previous courses. But again, like we did a couple slides earlier, I want to get rid of that denominator. So my denominator for both fractions that I have here and here is the same. I'm going to multiply everything by 1 minus x. And that will get rid of my denominator. So when I do that, if I do x over 1 minus x times 1 minus x, and think of it over 1, those 1 minus x's cancel out, and I'm left with just x, or x over 1, but I don't need the 1. And then down here, again, it will be the same thing. My x over 1 minus x will equal just an x. And then we have 1 times 1 minus x, so it'll be plus 1 minus x. And this is kind of nice, because if I look at this denominator now, I have x plus 1 minus x. Well, that means that my x's here, they're going to cancel. And we have x over 1, but that simplifies to just an x. Okay, so that one, even though it was very complicated, it looked like it wasn't too bad, and it worked. All right, so let's try g composed with f of x. And g is x, so we're going to have x over x plus 1, because I'm going to fill in f there. And then it's 1 minus x, so then it's going to be 1 minus x over x plus 1. And again, I want to get rid of the denominator. So I'm going to multiply everything by my common denominator, or in this case, x plus 1, or x plus 1 over 1. Okay, so again, if I have x over x plus 1 times x plus 1 over 1, remember those x plus 1's cancel, and it leaves me with x, or x over 1, but I don't need the 1. So x over, and then here, 1 times x plus 1 is going to give me x plus 1. And this is the same thing. They're going to cancel, so we're left with minus x. And again, it's the same thing as on the top. It simplifies out. So those x's, these will cancel. So I have x over 1, which equals a 1, or not 1, but an x, sorry. Equals an x. So that means that this problem is, these functions are inverses of each other. Next, we are looking at the existence of an inverse function. So not all functions have an inverse. In order for a function to have an inverse, it has to be a one-to-one function. So what that means is we know functions pass the vertical line test to be a function. It also has to pass the horizontal line test. So instead of just drawing your vertical lines, now you're going to have to draw horizontal lines. So if we look at this first function here, because when I draw that horizontal line, it passes more than 1 point on the graph at a time, this function does not have an inverse because it fails that horizontal line test. Now, the second function, you can see if you look at these lines, it's a little hard to see, but it does pass that horizontal line test. So that means that this function does have an inverse. And so if we know a function has an inverse, we can find that inverse algebraically by first taking away the function notation and putting in a y. So we make it y equals instead of f of x equals. Then we interchange x and y variables. So we swap x with y and y with x and solve for y. And that will give us the inverse function. Okay, so if we look at the function f of x equals 3x plus 2, if we were to graph this, it's a linear function. It forms a line, and it does have an inverse. So again, I'm just going to roughly sketch it, but if I had something like this, we would have, here's my coordinate plane, here's my line. This would have, it would pass the vertical line test, but then also that horizontal line test as well. So it does have an inverse. And so to solve for the inverse, to find the inverse, I'm going to start off, and instead of f of x, I'm going to make it y equals 3x plus 2. And then you switch your x and your y values. So now instead of y equals, it's going to become x equals 3y plus 2. And now we need to solve this equation for y. So I'm going to isolate y by first, I would subtract 2 from both sides. So now I have x minus 2 equals 3y. And then I'm going to divide both sides by 3. So we have y equals x minus 2 divided by 3. Or they may ask you to put it in function notation. So what I would do is instead of y, I would replace it with f of negative 1 of x equals x minus 2 all divided by 3. So that's the inverse for the first one. Now for b, if you were to graph it on the graphing calculator, and I'm going to try to draw it so it looks pretty good. It's kind of like a line that's going, it goes down, and then it goes down a little, and then it curves. Now, it is a little hard to tell, but because it has a constant increase or decrease there, it does pass the horizontal line test and the vertical line test. So it does have an inverse. And we're going to go ahead and find that inverse by making our equation y equals the cubed root of 7 minus 5x. And then we'll swap x and y. So now it's x equals the cubed root of 7 minus 5y. To solve for y, the first thing you want to do is eliminate that cubed root. So we are going to cube both sides. So now I have x cubed is equal to 7 minus 5y. Let's add 7 to both sides. So now we have x cubed plus 7 is equal to negative 5y. And then to get y by itself, I'll divide everything by negative 5. So g of negative 1 of x, or y, equals x cubed plus 7 divided by negative 5. And that is the inverse of the cubed root of 7 minus 5x. All right, so for C, again, I put it into my calculator just to take a look at the graph, and I would encourage you to do the same. When we graph it, it is going to look kind of, and again, this is just a rough sketch, something like this. But it does pass the horizontal line test because this is decreasing very slowly, but it is decreasing. So it will pass that horizontal line test. So we do have an inverse, and we can solve this equation. We're going to start off and make it y equals 2x divided by x minus 3. And now we're going to turn it into x equals 2y over y minus 3. And to solve this, the first thing we're going to do to solve for y is I want to get rid of my fraction. So I'm going to multiply both sides by y minus 3. Put it up top there. So we'll have x times y minus 3 is equal to, and they will cancel out on the right-hand side, to 2y. And then I need to distribute here, which is going to seem odd, but I do. I want xy minus 3x. And what I'm going to do is I am going to get both of my y's on the same side. So I am actually going to subtract xy from both sides. And I will end up with negative 3x equals 2y minus xy. Now you're probably thinking, we still got a lot of y's here, and we got to make it y equals. Very true. But I have a greatest common factor here of y. So I am going to factor out, I'm going to move up here, my y. So I'm going to have negative 3x is equal to y times 2 minus x. Because when I divide out my y, we'll get 2 minus x. And then now I need to get y by itself, so I'm going to divide both sides by 2 minus x. Oops, that's a minus in there. So y, or q of negative 1 of x, is equal to negative 3x divided by 2 minus x. It's a lot of work with these, but it's not bad, I promise. And I am going to erase, so I have more room to work on D. So if you need to, pause the video and write this down. Otherwise, I'm going to go ahead and erase a little bit. Okay, so now let's work on D. This one does have an inverse. So we're going to start off and we're going to say y is equal to x plus 1 over x plus 2. Or, now we're going to switch it. So x is equal to y plus 1 over y plus 2. And again, we're going to solve this really like we did with C. First, we're going to get rid of that fraction by multiplying everything by that denominator of y plus 2. So we end up with x times y plus 2 times or equals y plus 1. I am going to distribute that x, so we have xy plus 2x is equal to y plus 1. And we are going to put my y terms together and everything else, like the 1. I'm going to move the 1 over to this side. And I'm going to move the xy over to this side. So I'm going to end up with 2x minus 1 is equal to y minus xy. So I put the y's terms together and everything else on the other side because I know that now I can factor out a y here, a greatest common factor. So I'm going to end up with 2x plus 1 is equal to y times, y divided by y is 1, minus x, because y divided by y is 1 again. And then I'm just going to divide both sides by 1 minus x. And so y, or p of negative 1 of x, is equal to 2x plus 1 divided by 1 minus x. So it's a little bit of work, takes a lot of space up, but it does work in the end. It has an inverse, which is kind of cool. So when we look at E, we have x squared plus 2. We know x squared, or quadratics, when we graph them, because it's a positive x squared there, it's going to be a parabola. And it's going to open up. So we know it's going to look like this. It would pass the vertical line test, but if I'm trying to do that horizontal line test, it definitely does not pass that horizontal line test. So, and again, I just sketched the graph. I looked at it on my calculator. Because I know that it doesn't pass that horizontal line test, there is no function that exists. So it says to show why it doesn't exist, this is why it does not exist, because it does not pass the horizontal line test. So you can say it doesn't pass the horizontal line test. For our next one, the x to the 5th power minus 5x cubed minus 1. If we look at that graph, I'm going to make it kind of big so you can see. All right, this one's a crazy one, and it's one you wouldn't know off the top of your head, so you definitely, want to look at it using either an online graphing system or a graphing calculator. And I'm just going to roughly sketch it, but it looks kind of like this. Something like this. It's not perfect, but if I try to do the horizontal line test here, it passes the vertical line test, but it definitely does not pass that horizontal line test. So this is another one where there is no inverse for this function because it doesn't pass that horizontal line test. So if it says to show why, here you can see, you can show why it doesn't pass. And that is it for Module 4 for Math 026.